Okay, welcome to the third video in the series. 2C, we're exactly going over force. Now I'm going to read the scenario and I want you to mark it up. This is what we do. Carlos pushes a block of mass M across a horizontal surface at a keyword constant speed by applying a force F directly to the right. And so this little image of Carlos pushing this block of mass M directly to the right, and it's traveling at a keyword constant speed. And so a couple things: if it's constant speed, we know there is no acceleration. The velocity is not changing. If there's no acceleration, I know there is no, well, there's no acceleration. I know that F net equals 0. I don't want to say that there's no forces. I misspoke on that force. It's not that there's no forces, it's that the net force, the total forces, total sum of forces is 0. It has to be because there's no acceleration. So there's no acceleration, then the block is moving at a constant speed. And so let's see what Carlos is doing over here. So the dot says draw a free body diagram showing labeling all the forces, not components, the total forces or resultant vectors exerted on the block. Draw the relative lengths of all vectors to reflect relative magnitudes of all forces. Each force must be represented by a distinct arrow acting and pointing away from the dot. And so this is real quick and easy. This is just like regions, so we got to recall that if there's a block sitting there and it's getting pushed and it's at constant speed, of course the block in the y-axis, the F net and the y, 1, 2, 3, 4, 5 boxes. I'm just doing what I choose to be number of boxes. 1, 2, 3, 4, 5 boxes. These two vectors need to be exactly the same, the normal force and the force of gravity, because there's no acceleration in the y. They're exactly equal and opposite of each other. Now, in the case of the force being pushed, force directly, maybe let's make it 1, 2, 3, 4 boxes. I don't know. They didn't give me a scale or actual value. But I can say this is the force of Carlos. And of course, since it is traveling at a constant speed, something in the x needs to cancel out. And what is that force in the x that's canceling out as it's being pushed and dragging along this ground between this block of mass and the ground itself? Doot, 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 doot. Yes, you thought it correctly. Confident. Yes, Blue's Clues. Force of friction. And since it is net force is 0, meaning the sum of forces cancels out, this force F is going to be exactly the same length as the other one in front of it. Bam! What's up? So, nice easy diagram, really because of the key word that we focused in on here. Now, we're going to start with Newton's second law, which states that the sum of all the forces exerted on objects is equal to the object's mass times the acceleration. And so they're focusing entirely on the y. Let me go ahead and I want to zoom in here. Zoom in anymore? Okay. Way better. Let me zoom out a bit. Okay. Zooming out a bit and refocusing. Okay. Now we're gonna this is a line by line derivation, and so what we're really going is trying to state or explain what's happening here. Now, what's really happening is that the force, normal force is positive, the force of gravity is negative, and this really represents my sum of forces. Like, what am I really adding up? Remember we covered this symbol, this like weird E symbol, sigma, the sum of everything, and we're focusing entirely on the y right here, the y-axis. And so if we consider that my y-axis is just has a positive normal force and a negative force of gravity. Look at this, indicated here, positive normal force, the negative force of gravity. I'm adding these guys together, and that's going to equal my mass times acceleration in the y. Okay, and so here we're annotated normal force is positive, force of gravity is negative, adding them. to represent the sum of forces. That's literally all we're doing, is we're just adding them to represent that sum of forces. I can get a little bit out, so you can see a little bit more. Okay, good. Now, in this case, well, it's flying at a constant speed. Constant speed. We already said no acceleration. So then we can go here and say, well, the acceleration is 0. Okay? And then we can say the acceleration is 0. When you distribute that, then of course, well, the whole thing then goes entirely to a 0 as such. So then that's really indicating to us that this whole side on the left here, normal force minus the force of gravity equals 0. Because of course, the acceleration is 0. So really this is mathematically a free statement that these two forces, when they add to each other, will equal 0. So there is no net force in the y. And since these two are equal, if I bring one over to the other, then it really states the equality between the normal force and the force of gravity, the m times g, which is, we can assume from the picture in a free body diagram, and we drew it with the vectors. But here is what we need to get better at, is proving it mathematically. How do we know that these two vectors are equal to each other and that they will cancel out and eventually go to 0? Well, that's exactly what we're doing here. This final step, showing that since these are equal to 0, then Fn, if I add Fmg to both sides, then I get this, sorry for really small, if I'm adding to both sides, these guys cancel out, then f of n equals f of g. So this shows Fn equals f of mg. The magnitudes are the same. They're not this. Overall the force is not the same because of the different directions, but the magnitude, the values will be exactly the same. Now, let's go over here on this side. Well, we have a statement here that we're incorrect because some of it's true, some of it's not true. Yes, the molecular velocity is still constant. So again, I'm annotating. This entire statement here is going to tell me that acceleration equals 0. The net acceleration, that means ay equals 0, ax equals 0. Those are the connections we can make. That means there is force net equals 0. So that means the force, the sum of forces in the x equals 0, the sum of forces in the y equals 0. From this statement we can make those claims. Since my acceleration net is 0, y and x 0, f net 0, there's no acceleration. It doesn't mean that there's no forces, it just means that the forces that are being added up in the y equals 0, the forces added up in the x equals 0. And so we see once again in the y, it makes sense that the normal force and the force of gravity are going to add up to 0 because they are equal in magnitude, opposite in direction. This is going to be positive, this is going to be negative. Fn minus Fmg equals 0. That's literally what we just proved on the page before. But now, what Carl's statement goes wrong, and I'm going to cross it out in red and we're going to correct it, is stating that the force of friction equals the applied force of the pull. And you catch up a bit. And yes, even so, looking at this bit, letting you process that, this statement here, the normal force is actually not going to equal the force of gravity in this case. No. Both these statements are wrong. The net force exerted on the block must be 0, but what he's saying is literally what this case is before, and is different. Yes, the force applied equals the force of friction, normal force equals the force of gravity, but in this case, you have something pulled at an angle. Ladies and gentlemen, what happens here is, no, this pull is not entirely in the x. This pull is not entirely in the y. The components of it are. So I'm going to write F pull in the x And then there's an F pull in the Y. So now our statement entirely changes, because guess what? I now have how many forces acting in the Y? 1, 2, 3. So in this case, Fn plus F pull in the Y minus F mg equals 0. I have to account for the fact that I'm getting some help from the pull in the Y. That's going to take some off the normal force. So these two added together are going to equal the force of gravity. So Fn plus F pull equals the force of gravity of this mass. Not just the normal force, because now you have a component of the y-axis of the pull. And so this changes that equation entirely. So I was texting. Now, what happens in this? Well, in the x-axis, it's not the F pull, it is that the F pull in the x, only that component in the x-axis, not the whole thing, just the x component, minus the force of friction equals 0. Those two forces will cancel out each other in the x. Because remember, we still need everything in the y and everything in the x to be 0 separately to still hold true that the net forces and there's no acceleration in the y and the x, and the net is 0, meaning we're still traveling at a constant velocity. And that's going to be a theme we're going to see again and again and again throughout this unit. And so then I can take the statement, if I rearrange this by just pulling over the force of friction to the other side, the F pull in the x is going to equal the force of friction. And just to recap, because the next step is not actually doing this conceptually, but actually doing this mathematically. If I knew this angle here, then using this angle, F pull in the x equals F pull times cosine of theta. Because I do have the angle between the hypotenuse and the horizontal here. Cosine would be the adjacent over hypotenuse, and F pull x is the adjacent. F pull in the y is going to equal the hypotenuse, the resultant vector F pull, times sine theta. Because if they give us an angle and the actual force of pull, we can actually calculate the x and y components and then plug these into here as needed. For force of gravity, we only need the mass times the negative 9.8, and then, I mean, we're doing a lot of calculations, so conceptually we need to understand how these equations set up, and the next step eventually will be then to plug things in. We're coming to that eventually, dun 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 dun. So please do watch and review these videos as we amp up and prepare to tackle this exam. Thank you.